Okay, so it's great pleasure to have Rui-Dong from Switch University. He's going to tell us a topological vertex for SON, gauge series, and beyond. Please.
Okay, thank you very much. Thank you, Satoshi, to invite me and give me this very nice chance to present our work. So this talk is mainly based on the work with Hirotaka Hayashi. The paper was put on the archive in last December, and also I will probably mention a little bit about the work, the ongoing work with Satoshi. So let me start. So as you can see from the subject, from the title of my talk, the subject of this talk is about 5D n=1 supersymmetric gauge series with gauge groups restricted to SON type or G2 type. And I wish I can also give you some information about SU3 theory with Chang-Simon's level at 9 at the end of the talk. But it's mainly about SON gauge series. And what we use is brane construction with orientifold and also the topological vertex formalism, generalized in the way so it can be applied to the brane construction with such orientifolds. And also, if I just summarize the result in only one slide, it looks like this. So we consider SON gauge series, and the brane diagram looks like this. No, let me use my pen. So this is the example for So4 gauge theory, and as I mentioned about the topological vertex, it's a tool that allows us to compute the net crossover partition function from this kind of brane diagram. And because we have orientifold in the brane web, we have this kind of intersection point between 5-brane and also orientifold. So in addition to the traditional topological vertex, usually denoted as a C mu nu lambda, we also introduced a new type of topological vertex, and we use the notation V of mu in this talk. And also we have a dual vertex for this, and it's just the intersection point on the right, and we denote it as W of mu. So the topological vertex formalism looks like this. We just multiply these topological vertices together, and at the end we take the summation over all the Young tableaus that represent the internal degrees of freedom of a 5-brane like this. So that's a summary in just one slide. A
question?
Yeah, sure.
So this is a different theory with SU2 times SU2 theory?
You mean So4?
Yeah.
I will explain later, but it is really SU2 cross SU2, but we will have an extra factor, and it coincides with the U1 factor in the topological vertex characteristic. Yeah.
Okay, thanks.
Okay, so that's the summary. And I would also like to mention about the motivation here. Of course, we can do the calculation of the Nekrasov partition function, and with the localization technique, and we will get integral. And if we just do the integral, we will just obtain the partition function itself. But the reason that we want to do it in this in a different way in this topological vertex formalism is that we will see it, at least in the unrefined limit, it can simplify the calculation a lot. And for example, if we consider SUN or UN series, then the instanton configurations are labeled by Young diagrams or partitions in the mathematical terminology. For example, like the two instanton configurations for SU2 theory have 5 different configurations labeled by 2 tuple Young diagrams like this. So we also want to know if something similar can be done for SON or SPN gauge series. And in this talk, we will mainly focus on the SON gauge series. And also, I will mention it a little bit later, that we might be able to obtain some algebraic representation of the orientifold, as the effect of the orientifold will be included in the calculation as the vertex or vertex operator, as mentioned here, like the V mu. And the plan of the talk looks like this. I will first review the topological vertex formalism, and then tell you about the details of our proposal, and we will explain some technical details. I hope it's not too detailed. And then I will explain like the question asked by Kaiwen. We perform the consistency checks, and we look into like the partition function of So4 gauge series and so on. And at the end, we discuss a little bit about the future directions of this work or this method. Okay, let me explain about the 2 tools used in this talk. There seemed to be a little lag between my iPad and this Zoom presentation. I'm not very sure. So let me be a little slow. The first one we will use is the brane construction in type 2B string theory of 5D n equals 1 gauge theory. And then we use the topological vertex, and the topological vertex formalism was originally developed in the A-type model of topological string theory put on Torre-Calabi-Yau manifold. And but since we are putting orientifolds in the brane construction, so we need to generalize the framework and introduce some new vertices. Called we will call it O vertex in this talk, and it's denoted as a V mu or W mu here. And the brane construction looks like this. So we are considering type 2b superstrings, and we used like a D5, NS5, and also other PQ5 branes. So the direction of 5D theory is in this 0, 1, 2, 3, 4 direction, and well, we put the PQ5 brane in the PQ direction, like parallel to the vector of PQ, and so we can see that all the non-trivial information of this construction is just encoded in this 5 and 6 direction. That allows us to draw a picture of this of the brane configuration, and well, it's several examples are given below. And well, if we do not put orientifold in the calculation, in the construction, then we can read the gauge group. For example, if we have a 2 D5 branes, then we have a SU2 gauge theory, and if we have 3 D5 branes, then we will get SU3 gauge theory, and similarly, the diagram looks.
Yeah, it looks SO6
this
and
is
SO8.
Yeah, this is wrong.
Okay. Okay.
This is the. Yeah, this is SO6, and this is the SO8. Yeah, so in SO2N gauge series, if we have N D5 branes, and by using the orientifold, we get SO2N gauge series. And well, I will also explain about the diagram for SO odd. Well, we need to do some hexing in order to compute the SO odd series in our formalism. And now we well, we go to the review of a topological vertex. It's a tool for the computation of the crossover partition function, and it works in the way like a Feynman diagram. It has 3 sub-indices, and also diagrammatically it has 3 legs, and they are labeled by Young diagrams. And well, it looks like this. If we have a diagram looks like this, then we have a lot of vertices. We have a lot of intersection points of these 5 branes, and well, they are the basic ingredients usually has 3 legs, and so we truncate the diagram, and we give this kind of 3-leg part the name of a topological vertex, and assign this topological vertex function C mu nu lambda to the vertex. And then we just multiply these vertices, these topological vertices together, and sum over all these internal Young diagrams. Of course, they are weighted by the Kähler parameters, and in terms of gauge theory, they correspond to the Coulomb branch parameters, and in the language of string theory, it corresponds to the exponential of distance between different branes. And well, the topological vertex is well, it doesn't. Well, I'm not sure about this. It doesn't look very complicated. Well, it can be written in terms of symmetric polynomials, and well, in the case, in the unrefined case we consider here, it is completely written in Schur functions, and also like skew Schur functions, and well, it's very easy to compute the topological vertex itself. Well, and we also have this kind of a little weight in front of the vertex. And well, there's a technical point here about the framing factor. There's a thing called the framing factor, and we have also we have to also multiply it to the summand of the well, to calculate the partition function, and well, the power of the framing factor, it depends on kind of local geometry of the toric diagram or the brane diagram of the brane construction. It looks like this. If we consider the framing factor associated to this Young diagram lambda, then we consider the vectors sandwiching this Young diagram, these two vectors, and we compute this kind of vector product of these vectors, and then well, we multiply this framing factor to the summand of the in the calculation, and we take the summation over all possible Young diagrams representing the degrees of freedom of the internal lines in the brane diagram to find the final expression of the Nekrasov partition function. And well, let's see. Let's look at some examples. The first one I would like to maybe there's some lag. Okay, came out. Okay, the first one is the U1 theory, or sometimes it's also called SU1 theory because it doesn't. Well, it only calculates the instanton part of the U1 Nekrasov partition function, and it doesn't depend on the Coulomb branch parameter. And well, we can simply assign the topological vertex to the diagram, and well, use the Schur function. We can easily simplify it to the final expression. Looks like this. So this, well, the final answer is written in terms of the so-called Nekrasov factor. And also, if we consider SU2 theory, the diagram looks like this. And now we have, because we have four vertices, so we use 4 topological vertices and also some framing factor. Then we will find some plastic exponential looks like this, and it is multiplied with also some Nekrasov factors, and we can understand the calculation as so this part, it doesn't depend on the Young tableaus, so it actually corresponds to the perturbative calculation of the one loop factor, and also the later half is the instanton part of the Nekrasov partition function. And of course, the instanton counting parameter is related to the length of the D fibrils, like this, the distance between NS fibrils. Okay, so yeah, as I explained in the example of SU2 gauge theory, so actually the Nekrasov partition function can be well factorized into several parts, and what's reproduced in our calculation is some of the perturbative factor and the whole instanton part. Well, the perturbative part can again be written as the product of the Cartan part and the part that depends on the root of the gauge group, well, the Lie algebra of the gauge group. And well, the Cartan part depends on the rank of the gauge group, but actually in the topological vertex calculation, it will not show up. And the root part looks like this. It's again returning the plastic exponential, and here I give the expression. Well, it's called the refined expression on the generic omega background, but in this case, we will consider the special case. In this talk, we will consider the special case with epsilon1 plus epsilon2 equals 0, and it's called the unrefined limit of the Nekrasov partition function. Well, we will see that it simplifies the calculation a lot in the SON gauge theories. And of course, the instanton part counts the instantons constructed from the ADHM construction of the instantons. And well, I guess I don't have to motivate my audience to study the ADHM instantons. And now I explain the details of our proposal. So as I said before, we introduced a new topological vertex. It's denoted as this V of mu. So the subdiagram that corresponds to this topological vertex looks like this, and we will see that it's an intersection point of this 2,1 fibrine and the orientifold, and because we only have one fibrine in this sub-diagram, we have only one leg of this vertex. So and so it only has one subindex of in the function, and so we can write it in this form. It's P mu over some Q Pohokamma factor, and well, the denominator only depends on the size, well, on half of the size of the Young tableau. And P mu is well conjectured to be a polynomial. We computed a lot of precise, well, a lot of concrete cases, and found out that it's always a polynomial, but we cannot prove it even from our proposal at the moment. And our proposal says that this p mu, well, it's expected to be a polynomial. It can be computed from a vertex operator, O. We call it O vertex, and it's this kind of expectation value of the O vertex. And we have some fermionic bases, well, 2D fermionic bases that's labeled by Young tableaus. And by extracting out the corresponding order of P, we can compute this polynomial in details, and this O vertex, it actually looks like this. Well, although this mu, mu here is formulated in fermionic basis, but the vertex is a completely bosonic one, and we can use the free boson oscillator to write it in this form. And because only like j of 2n, or like the square of jn shows up, we can immediately say that if mu is a odd size Young tableau, then this polynomial, or this function p mu will vanish. So so this mu can only be even sized in the calculation.
So you just give the answer, but how do you determine this form? Are you going to explain?
Oh, yes.
Okay.
But before that, I want to, yes, let me first explain about the fermionic basis. And well, we all know the free fermion and the free boson, I guess. So if we use a free fermion and the free 2D free fermion and free boson oscillator, and we use the so-called Frobenius basis of the Young tableau. Well, it's basically the length of each row, but well, started from the diagonal line. Well, it's this distance between the right hand and the diagonal line. So the Frobenius basis looks like this for this Young tableau, and then we can use this kind of fermionic generators to write down the fermionic basis. Well, and use it to compute the O vertex, as I mentioned before. And of course, this fermionic basis is a complete basis. So if we sum over all the Young tableaus, it will be 1, and that will simplify the calculation a lot later. And now I want to first play a little bit about with this polynomial p mu, and I gave some explicit expressions of this p mu here. We can see, for example, if the Young tableau is empty, it's 1, and if it has 2 boxes in a row, it's minus of q, and so on. Well, so we can see it's it always takes a form of a polynomial, and we checked this back to up to the order of 10, like the size of the Young tableau to be 10. But unfortunately, we do not know what the polynomial is at the moment. But we observed some interesting points of the interesting properties of this polynomial. For example, if all the boxes lie in just one row, then it can be easily calculated in this way. And well, actually, we can use the special property of the fermionic basis like this to even prove this this formula from the vertex operator, expression well proposed here. And also we have another observation that if we put one box in the second line, it will be this, well, the value of the polynomial will be the same as the well, the polynomial of the Young tableau just in one line, but with two less boxes. But so far I don't know how to prove it, but you can see it really works in this way. But more generally, it's quite complicated to compute the explicit expression of this p mu. Well, of course, we can do it in Mathematica. It's not that slow, but well, we also observe the kind of duality property in this polynomial. So, for example, if we know the expression of this p of lambda, then we can easily find the expression of this p lambda transpose. It's just well, we just need to change the sign, and also the power will be like well, if the power is I, we subtract this I from a total power that appears here, I think. And well, it can kind of be proved in our well, in our vertex operator formalism. Like, for example, if we consider the case with all boxes lie in just one line, and also its transpose is all boxes lie in one column, then we can use the automorphism of the free fermion, which change the basis from lambda to lambda transpose, and it actually changed this free boson, well, give the free boson just a one minus sign. So it acts on the all vertex in a very simple way to just change the sign here, and then it's very easy to find the expression of, for example, this polynomial from the above calculation, and we can easily prove that this polynomial is always one from this formula. Okay, so that's kind of duality property. Well, yeah, it will at least allows us to only compute half of the polynomials, and also we have a recursive relation in the q goes to 1 limit. I couldn't find the recursive relation in the more general. Well, I couldn't find the rule in the more general case, but in the q goes to 1 limit, we can see that up to a sign, this polynomial actually counts the number of ways to generate this Young tableau mu with only like this kind of two boxes in one row and the two boxes in one column. So for example, if we consider this kind of 2,2 partition, it can be generated either like this or this in the from this two kinds of Young tableaus, and so the q equals 1 limit of this polynomial will be 2, and indeed we can see it's 1 plus q to the cubic power, so it's 2. And also we can, if we consider the q goes to 1 limit, then we can easily calculate higher order polynomials from lower ones. For example, this kind of 2 to 2 partition can be decomposed into this one and this one. So we can add add these two polynomials in the q goes to 1 limit together to find the answer of this higher order polynomial. And indeed, it's 3. Although we have a minus sign we have an overall minus sign at the end. And it might be, this is kind of a recursive relation, might be related to the fact that this polynomial can be determined from this kind of vertex operator, and this kind of free boson generators, it generates this kind of Young tableau, and it kind of adds this kind of two box Young, add 2 box at one time to the Young diagram to generate higher order polynomials. So this is a recursive way to determine the polynomial in the q goes to 1 limit, and also, but we couldn't determine the sign in this recursive method. But the overall sign can actually be determined from another recursive way. First of all, we know the sign of this p polynomial with all boxes in just one row, and the rule is that if we move one box from a line, from ith line, from ith row to I plus jth row, then the sign actually changes. There's only one overall sign, and all the coefficients have the same sign in our observation. I don't know how to prove it, but anyway, the overall sign changes by -1 to the jth power from our observation, and in this way, at least in the q goes to 1 limit, we can completely determine the polynomial in the recursive way. But actually, as I will explain later, we don't really need this polynomial in the calculation of the Nekrasov partition function. We can simply use the vertex operator itself, and it's way more powerful to use the completeness of the Fermionic basis and the commutation relation of the vertex operator, and we will find it to be easier to do the calculation. But if we just use the traditional topological vertex formalism, we really need to obtain the explicit form of this kind of polynomials. Okay, so another comment for this symmetric polynomial, for this polynomial, is that it might have something to do with the symmetric polynomial. I'm not really sure at the moment. So actually in the SUN case, if we consider the refined topological vertex and tune the parameter appropriately, well, if we tune the parameter appropriately, then the refined topological string partition function will give the McDonald polynomial or McDonald function in general, and so we can expect that at least in the unrefined case, we might be able to get some like Schur function, but because we are computing like a D-type SON gauge theory, so maybe it's related to D-type McDonald function. I don't know. But one interesting observation is that there's this kind of formula in the textbook of Schur function saying that the Schur polynomial can actually be calculated from the orthogonal Schur polynomial. Well, that is the say D-type Schur polynomial, and when we take the summation to get this Schur polynomial, only the even size Young tableau shows up in the summation. So it might have something related to our polynomial P, and well, recall that our polynomial P of mu also is only non-trivial when mu has an even size, well, even number of boxes. Okay, that's enough about this polynomial. Let's go back to the main subject of this talk. So we got the new vertex, new topological vertex, and we can simply use it to calculate the necrosal partition function. And what we use, practically used in the calculation is that we can just use this form, the vertex operator form, and we also use the we can also use the vertex operator form of the Schur function, the skew Schur function. And for example, in the derivation of the Cauchy identity of the skew Schur function, we can, well, substitute in the vertex operator form of the Schur function, and we do the summation. We do the summation by using the completeness of the Fermionic bases, and it reduces to the well, this kind of expectation value of the vertex operators, and by well, because well, we can see this is an explicit expression of the vertex operator V, and V plus is annihilating one, and the V minus is a creating one. So by exchanging V plus and V minus, well, with the Becker-Campbell-Hausdorff formula, we can got some factor, and we use the completeness of the basis, and we can, for example, derive the Cauchy identity. And in the case of SUN gauge theory, what we need is this kind of specialization of the Cauchy identity, and what we obtain at the end from the previous calculation is this kind of one loop factor times the Nekrasov factor. So that's how the structure of the Nekrasov partition function shows up in the calculation with the vertex operators. And well, I give some details of the Nekrasov factors. Well, it's also related to the Schur function well, in the horizontal direction, that is the color brane or the D5 branes. And now, finally, I can answer the question of Satoshi, how we got the proposal, what the logic is behind our proposal. For example, if we consider the So4 brane diagram again, we can consider the perturbative part, and well, by doing that, we just set these two Young tableaus to be empty. That is to turn off the degrees of freedom on the well, kind of turn off the degrees of freedom on the D5 branes, and then we get the product of the left half diagram and the right half diagram, and of course we know the answer of the SO4, for example SO4 or even SO2 and gauge theory, the one loop part of the calculation. So we can just substitute the vertex operator form of the a topological vertex in the calculation, and it looks like this. Well, we can see that we can do the summation of the Young tableaus with the completeness of the Fermionic basis, and the end it's just a very simple factor here. And well, this is another one loop factor, and because we know the answer of the one loop factor, so we can use this no answer of the one loop factor to determine this O vertex. And that was the form of the O vertex I showed you before. And so our proposal is that by choosing this O vertex that satisfies this perturbative calculation, it can reproduce the instanton partition functions. And well, one comment that is not really needed here is that there's a very convenient BCH formula that can be used in this calculation, and well, recall that our well, the shoulder in the O vertex looks like this, and if we use a variant of the BCH formula, it's not hard. Well, it's very easy to do the computation with this O vertex. So another comment here is that there's a proposal by Kim and Yagi back in 2017, like they proposed the topological vertex for the like for the intersection point here of two fibrons and the orientifold. So their proposal was saying that we should do this kind of mirror. Well, we consider this kind of mirror expansion of the diagram and apply the usual topological vertex formalism to this kind of diagram by being a little careful about the Fermi factor in the calculation. And for example, the partition function of the SP0 theory is really trivial. And so we can consider this diagram of SP0 theory, but with non-trivial external legs, and do a geometric transition to obtain this kind of diagram. And if we pour this this part to the infinity, then we get this sub-diagram that we need for the computation in our SO2 and gauge theory and this part we call it the O vertex in our calculation. And well, we can really compute it in this way, and we check that the P polynomial obtained in this way also well matched with our calculation. And let me skip to the consistency check part. So first, let's consider the So4 theory. And as I mentioned before, it's actually equivalent to this diagram times this diagram times this diagram. And this is a U1 factor across SU2, well, two SU2 gauge series. And well, there are these two SU2 gauge series already decoupled. Well, of course, we can use the O vertex mentioned before, and we checked the one instanton and the two instanton expressions really matched with the known result in the localization calculation. And also for SO6, well, it's isomorphic to SU4, and the equality works in this way. Like we have this kind of subdiagram, and it really shows up in the subdiagram here in the SU4 theory. And well, we will have another Coulomb branch parameter. It's encoded in this P, that's a distance with the orientifold. And again, we checked the one instanton and the two instanton results that matched with the localization result. And also we did the calculation for SO8. Again, we checked one instanton and the two instantons. One comment is that because our proposal works in the way that the perturbative part automatically matches with known result in the literature, so we only need to check the instanton parts. And more generally, if we consider SO2N gauge series, then we just need to add ND5 branes on the top of orientifold, and we can do the calculation, and the vertex operator part involved in this calculation generally looks like this. And well, it's all very similar. We can try to compute it, and we call it M factor in the ongoing work with Satoshi. And well, one comment here is that, for example, in the calculation of localization integral, actually, if we consider the unrefined limit, we can effectively choose the it seems that we can effectively choose the poles, the JK poles, like in this way, probably, and they really forming a Young diagram form, and we can, at least in the calculation of one and the two instantons, see that each residue matched with the contribution from our topological vertex calculation. And in general, well, we expect that the topological vertex formalism will give the well, the closed form expression of the of each residue in this localization integral. And for SO odd theory, actually we need to do something different. Well, it's similar. We consider this kind of brane diagram, and but now we've set this Coulomb, well, this scalar parameter t here. Well, it's a distance between this empty d5 brane with the orientifold. And we have to take the t goes to 1 limit at the end of the calculation. So for example, the perturbative part looks like a mixture of SO2n minus 1 theory and SO2n plus 1 theory. And we can see the string here that connects with the empty brane. Well, this empty brane in the limit that t goes to 1, which is the distance 0 limit. And so it will be just located on the orientifold. So the string stretching between usual d5 branes and this special d5 brane will give the additional roots. Looks like this in the SO2n plus 1 calculation. And well, again, we checked the 1 and 2 instanton calculations in SO5 and SO7 gauge theories. Well, one may concern that the t goes to 1 limit could be hard to be taken, but well, first of all, if we do the expansion, like if we use the traditional topological vertex calculation with the symmetric polynomials, we can see that, for example, the perturbative part, it looks like this. It's actually symmetric between t and the t inverse, and also whenever t appears, t or t inverse appears, we will have p. So if we do the expansion over p, we will see that the power of t is actually suppressed by p. So it's always possible to, well, it's always just, we can always justify to take the limit of t goes to 1 in the, well, to calculate a finite order in the expansion of p. And more generally, if we use the vertex operator calculation, then well, this limit is even easier to be taken, and we don't need to do this truncation. So it's not a problem in summary. And also, like orientifolds and this kind of Higgsing can be used in the calculation of the G2 gauge theory. The brane diagram is given in this paper. Well, we can apply the O vertex in the left half, and also the we also need the Kim-Yagi prescription in the intersection point here. And for example, the perturbative part looks like the mixture of SO6 and SU4, and well, by taking this t goes to 1 limit again, we can see that the perturbative part really reproduce the G2 root structure. And also we checked the 1 and 2 instanton calculations, where the 2 instanton calculation actually was tested by matching with the blow-up results. And also, well, actually I didn't mention, but there are 2 different ways of the brane realization of G2 series, and another one looks slightly different like this. And for example, the perturbative part looks like a mixture of SO8 and SU3 series. And well, anyway, we can do the same trick to calculate the 1 and 2 instantons, and it again gives the same answer. And what's more interesting is that we actually can also use this vertex to calculate the SU3 gauge theory with the transience level at 9. So the diagram looks like this. Actually, it's a S-dual configuration. We can actually apply the O vertex and also the Kim-Yagi prescription in the brane web. And well, again, I have to say that the series expansion is really slow, so it does seem to be a good approach, but also the vertex operator approach is also more complicated. It looks like the sandwich of two vertices and a bunch of V minus and V plus vertex operators. Well, there might be some good version of the BCH formula that can do this kind of computation very easily, I hope. But at the moment, it's still not very easy to, well, not that easy to do this calculation for this SU3 at transience level 9. And well, similarly, we can add flavors like by putting external D5 branes in the diagram, and we can do the same for SON gauge theories. And well, the vertex operator part just looks like this, and well, we can see it's almost the inverse of the M factor. So if we can really get the closed form of the M factor, then we can write down a well, very analytic expression of these of the Nekrasov partition function of these gauge theories. Well, at arbitrary number of instantons, I guess. So in summary, what we did is we just proposed a new topological vertex called the O vertex, and it can be used to calculate SON gauge the partition function, Nekrasov partition function of SON gauge series, and also like G2 and probably well, hopefully more efficiently for SU3 gauge theory at transience level 9 in the future. And so what we want to do, and this is also what we are working with Satoshi, is that we think we can write the M factors in a closed form. So the analysis will be more analytic and well, more controllable in the future, I hope. And with that kind of analytic form, we hope we can compute the QQ characters, which is related to the AGT, or the S-dual version of the AGT, that is the quiver W algebra of the SON gauge series. And actually, we really don't know if it works well in the SON case. And of course, we want to do the refinement in the future, but it might be, I don't know, it might be different, because the number of pores in the localization formulation is much more than the number of young tableaus. So I don't know, we might need to add some additional contributions in the calculation. And also probably we want to know the topological string origin of the all vertex in the future. And also like, well, it's related to maybe the computation of symmetric partition function of symmetrical matter, because it also involves the all vertex, but we probably need to introduce more novel type of topological vertices in the future. And well, I hope it will help us to analyze the gauge theory in more, how to say, rigorous and convenient ways in the future, especially for the SON gauge theories. Okay, that's all. Thank you very much for your attention.
Okay, thank you very much. Questions from audience?
Question?
Yeah, yes, please.
Thanks for the good talk. So the last page, you read the prescription be local. What do you mean local?
Local means that each vertex in the diagram can be associated. Well, we can just assign a function to the vertex. So, well, it looks like we can just multiply several functions like a v of mu and also like c mu nu lambda together and take the summation of Young tableaus, but I doubt it also works in the refinement case. I don't know. So
yeah, I mean, if you perform JK residue of SON ADH quiver, there are much more poles than the Young tableau. I mean, we discussed it with Rui-Dong just like half year. I'm sorry, half hour ago, but yeah.
Yeah, what I mean by the local is that for each of this, for each of this kind of vertex, we can just assign a function and do the usual topological vertex calculation.
Okay, I see. So one more question is about the SO7 gauge theory. So you know there is another Young diagram summation formula for the SO7 differential partition function, right? So
yes.
I'm wondering whether that formula is when computed out is actually the same with your Young diagram summation formula here.
I'm not sure, but
no, it's not the same. It's not the same. Yeah, I mean,
but for G2, you said it's the same.
Yeah, for G. So in this Korean group, they computed SO7 G2. SO7 case, if you take unrefined limit, the formula is very different. But we check at each instanton level, up to 4 instanton, it coincides. And then for G2, expression exactly coincide. Some others coincide. The expression is, if you take unrefined limit this Korean group result, it coincides with our formula.
Yeah.
So you mean the G2 formula?
Yeah,
in the unrefined limit is the same.
Yeah, so G2 can be refined.
Okay,
so and SO7 you checked it's different.
SO7 is more like just the traditional localization. Well, it's in the form of the localization calculation.
So we have now a closed formal expression this SON instanton at unrefined limit in terms of Young tableau. But that
I see.
that
Great.
really coincide with the ADHM formula, not the Korean groups. Korean
Yeah,
group
yeah.
use SU4.
Yes, they built from SU4.
Yeah.
Our is really
Okay,
ADHM.
okay.
Yeah.
I see. Thanks.
Yeah, probably that means we can have some different kind of brane diagram for SO7. I'm not sure.
Yeah.
So can I ask a question, Rui-Dong?
Yeah.
Yes. Yeah, so first, thank you for your nice talk. So I just have a very small question. So I guess you can also generalize to SP gauge groups, right?
Oh yes, that's what Satoshi is trying, I guess.
Okay, I see.
Yeah.
So it's very different. So is some duality between SO and SP? I'm just wondering. There's some
duality.
Maybe not. Okay.
Is there any known duality between SO and SP?
Well, sorry, it's in different contexts. So yeah, so I'm just wondering. Yeah. So
okay.
Because basically they're yeah. Oh, so you mean that
I don't know.
You are working on this.
Yeah, we are.
Okay.
Well, focusing on the technical aspects at the moment.
This is just my speculation that at the unrefined limit, at least we can obtain the instant of partition function in terms of Young double, sum over Young double, tuple over Young double. That's my expectation for even SPN, unrefined limit. But
okay.
But
yeah,
whether or not we can give the
Okay, thanks. Yeah.
I have one question since there are many experts in the audience about this blow-up equation that you mentioned that the G2 result is matched with blow-up equation. I don't know whose result is this. Yeah, this one. G2.
Yeah. Well, I remember it's from well, also the paper of Korean group, like they had the 5D blow-up equation for like SO and probably G2. I
see. So the blow-up equation for SO type is already known.
I think so. Yes, in 5D case.
I see. How about SP?
It's also known, right? I think it's known. Yeah. I think it's in the same paper. I don't quite remember.
Okay, I see. So essentially, recursively, you can construct even refined instant of partition function S1 and SP by using
recursively you can
recursively blow-up equation.
I think recently there's a paper by Song-Su and Hicho. They have they consider lots of cases using blow-up equations. They basically because they know the prepotential, and then basically you just need the prepotential and you can write down the blow-up equations.
For any gauge group?
For any gauge, well, for many gauge groups. I'm not sure if it works for any gauge group. Okay.
Okay.
Yeah.
I think for any, they both work.
Okay.
I see.
Okay.
I see.
Yeah.
Yeah, but the blow-up equation trivialized in the unrefined limit. I remember we don't have a unrefined version of the blow-up equation.
Yeah, you can only do on the refined level.
So
you cannot just solve the unrefined partition function. It must be refined.
Yeah, so it's hard to start from our result to get the refinement down. we have to guess.
Sorry, what's the hard part if you want the refinement of your suggestion? You have to add some preferred direction in the diagram or what?
No,
no, it's just that we have a lot of pores that cannot be represented by Young tableaus. I think that's a reason.
Yeah, this is the case.
Even from the topological vertex, you cannot do the refinement.
Well, if we want to match with the localization result, then well, we can reproduce maybe part of the contribution, like those labeled by Young tableaus. I think that's what we can do. I don't know.
I mean, so I can make a comment, but at unrefined, so this result, Rui-Dong result actually coincide with the how to say ADHM localization result. And at the unrefined limit, you can pole is one-to-one correspondence in Young tableau of the ADHM formula.
Yes.
However, if you take the if you refine if you try to refine the result, if you do the JK residue, there are lots of pole appears. There are other than Young tableau. It's more like a 2D random walk on the epsilon 1, epsilon 2 direction somehow. So, and also it also depends on SO odd, SO even. And SO odd case, there's some holonomy saddle also appears in refined limit. Sorry, refine if you try to refine. So at least, I mean, you cannot simply generalize this topological string to refine topological string. That's so far my impression.
But what I mean is that even in the ADHM description, you can still have a close expression at specific instantons, like 1 or 2 instantons is possible. And you can, I mean, simply check your result with that.
Yes, of course we can check.
Yeah,
but,
right.
How to say? Well, in the unrefined limit, you can see, well, the analytic expression is really the same.
Okay.
But in the refined case, well, of course we can, I don't know, maybe we can like do something strange and require it to reproduce the result, but it will look quite different from the usual topological vertex formalism, I guess.
Yeah, that's my impression.
Sorry, what's the problem for the refinement?
So for instance, if you try to apply JK residue on this ADHM formula, then there is some pole that will give you residue which is proportional, for instance, Q minus T. And if you take unrefined limit, this term becomes 0.
Okay.
But unrefined, so refined case, there is some non-trivial contribution.
Yeah. So for ADHM description, I know it's very well established. I mean, maybe even though there are many additional poles, maybe cancel each other, but the result is well known.
Yes,
My question is that in your formula, your new
but only in the unrefined limit that we can label all these contributing pores in terms of the Young tableaus. Otherwise, it's not in that form.
Yeah.
And from the calculation of topological vertex, you will naively expect that everything is written in terms of Young tableaus. So it's not straightforward to generalize to the the general refined case.
So your operator V or something is based on the gas from ADHM. That's why you cannot get it. Oh, it's hard. Is that a
well, we guessed it from the perturbative part of the calculation.
All right.
And yeah, it doesn't know the ADH formula, ADHM construction at the very beginning, but if we just do the computation at the end, we will see that it will produce the ADHM construction in the unrefined limit. But in the unrefined limit, something special happens. Some of the pores, some of the instanton configurations become trivial, and so we do not have to consider about them. But once we go to the refined omega background, then they will be contributing again. So we have to take them into account again, and naively, well, it looks something different to be obtained in our formalism, in this topological vertex formalism.
I see. So your answer is that, I mean, naively look at the answer from ADHM. There are extra contributions that do not contribute, do not capture by your formula.
Yes, you can say that.
I see. Okay, thank you.
Any other questions? Okay, if not, let's thank the speaker, Rui-Dong, again.
Oh, thank you very much.
Thank you very much. So I'll stop recording.